Sn1. So, an Sn1 reaction. Substitution, nucleophilic, unimolecular. Unimolecular means only one species is involved in the rate-determining step, and that's the alkyl halide, the electrophile. What happens in an Sn1 reaction? There's a substitution, right? But the first step is the leaving group leaves, right? What are good leaving groups? Things that are stable. I-, things that can do resonance, things like that are good leaving groups. Leaving group leaves. That's the slow step. The nucleophile is not involved in the rate-determining step at all, right? Why is this a slow step? This is a slow step because when this leaving group leaves, you leave a carbon without a full octet. Carbon without a full octet is going to be high in energy. So it's going to take a lot of energy to do this, and you're going to make a high energy intermediate. What's the hybridization state of a carbocation? It is sp2 hybridized. In this case, that means it has an empty p orbital. If it has an empty p orbital, the nucleophile, which a lot of times is the solvent, right? Because we call these solvolysis reactions, polar protic solvents. Polar protic solvents, let's say something like, water, right? Polar protic solvents. It can react either from the top or the bottom. So if this was an asymmetric center, if this was RS, in the products, you're going to get a mixture, a 50-50 mixture of R and S. The stereochemistry for an Sn1 reaction gives you a racemic mixture, a 50-50 mixture of R and S, because the hybridization state of a carbocation is sp2 hybridized. And it's stabilized. Why is it sp2? Because this bond angle is 90 degrees. Empty orbital, electrons and bonds, it wants to be as close as possible there. So the rate is a rate constant times the concentration of the alkyl halide, the electrophile. Notice, the nucleophile is not in the rate determining step at all. It's not in the rate law. All right, so how do we know if the reaction is going to be Sn1 or Sn2? We look at the alkyl halides. So I've drawn a couple here, possibilities. Primary, secondary, tertiary, primary allylic, tertiary allylic, and primary benzylic. So if we look at this, we can eliminate what's possible just by understanding that we need to form a carbocation in an Sn1 reaction. We will never form a primary carbocation. So primary alkyl halides only do Sn2. Secondary, right, can do Sn1 and 2. Tertiary, just Sn1, right? It's too bulky to do an Sn2. It's too sterically hindered. Primary allylic, Sn2 for sure, and Sn1 though, because you form a carbocation that can be stabilized by resonance, by pi bond resonance. Tertiary allylic, if it's tertiary, it can't do Sn2 at all. So you're only stuck with Sn1. Anything tertiary won't work for Sn2. Primary benzylic will work for Sn2 for sure, but also Sn1 because of that resonance stabilization of the carbocation. So pretty much everything works for Sn1 except for those primary alkyl halides. Sn2 is worried about the sterics. Sn1 is worried about the stability of the carbocation. Free energy diagram. So this is showing all the steps in an Sn1 reaction. There's always going to be more than one step in an Sn1 reaction. The first step, or doesn't always have to be the first step, but the step where the leaving group leaves is always the slow step. Why is it the slow step? Because what are we making? A carbocation that doesn't obey the octet rule. So it's going to be high in energy. It's going to take energy to do it, and we're going to make a high energy intermediate. Here you see the carbocation again. In this case, the nucleophile is the solvent, polar protic solvent. It can react from the top or the bottom. So you can get a racemic mixture, or you're going to get a racemic mixture in this case. All right? Nucleophile reacts. You're not done yet, though. There's also a deprotonation step, and you finally get your alcohol, in this case, HCl. First step is the slow step. Only the alkyl halide, only the electrophile is involved in that step, because you're making the carbocation. Lots of energy, high energy intermediate, sp2 hybridized. polar protic solvents. Polar protic solvents, this is called solvolysis. And the solvent acts like the nucleophile. All right, just to reinforce the stereochemistry idea, if you started with, this is a tertiary alkyl halide, bond to 3 different things. So this could be RS, in this case it's R. If this leaves, if this leaving group leaves, it goes from sp3 to sp2 hybridized. It's flat, planar, right? Empty p orbital. The nucleophile, the solvent in this case, can come from the top or the bottom. What that results in is both enantiomers in this case. You would get both R and S. You get a 50-50 mixture, you get a racemic mixture. So remember, that's one of the things you can look at. If you look at the products and you see I had R in the starting materials, and I look at the products and I see racemic mixture, what kind of reaction must it be? Sn1. If in the starting materials I see R, and then in the products I see S, that's inversion. So it must be an Sn2 reaction. All right, so these are the kind of things that you can tell the differences between these two.